Next up, we have Dan Gaines of NASA JPL presenting on the Mars 2020 On-Board Planner. Dan, it's all yours.
Thank you very much, and hello. Today I'll be talking about the Mars 2020 On-Board Planner, and we've talked about this work in a couple past flight software workshops, so I won't go into the details of the algorithm.
And we just, can you unmute?
Oh, thank you. Sorry, didn't realize I was muted. So thank you. So I'll be talking about the Mars 2020 Onboard Planner. And we've talked about this system a couple times at previous workshops. And so I'm not going to go over the same material, but instead I'm going to focus on how some design and implementation decisions that we've made to make a balance between high performance and responsiveness of the system while still playing nice with other tasks the flight software has to do within our limited computational constraints. Next slide, please. To begin with, I'm going to give you just an idea of the kinds of things that the onboard planner has to worry about by showing you what a typical simple example of a sol in the life or a day on Mars looks like for one of our rovers. And the actual specific activities it performs will vary based off if it's driving this day or it's doing proximity science or sampling. But some of the overall main points are common to those different types of activities. So in this case, I'm showing you what a drive sol looks like. And we begin every sol with an uplink window where we send our command products to the system. And then we usually have a period of engineering maintenance activities, managing onboard sequences and data products. And then if we're going to drive, we usually begin with what we refer to as a pre-drive imaging block, where the scientists will target observations at the area that the rover is currently in before we drive away. And towards the top of the slide, we see an exploded view of what that might look like. We usually use the SuperCam instrument, the mass cam, navigation cameras. And then we have some margin because, and we'll talk about this, that predicting the amount of time things take to execute on Mars has some uncertainty. And so we add some margin for duration to make sure things finish in time. But if we're still underestimating how long things take, if they go much longer, then we have a cleanup block where we make sure that instruments get powered off and shut down and put into safe states before we move on to the next phase of the day, which in this case is driving. So then we drive, and usually when we drive, we have our ground penetrating radar instrument going, so we see RIMFAX in parallel. At the end of the drive, we'll do some post-drive imagery to document the scene that we're at. And then we have the first of a few different communication passes where we relay our data through one of our orbiters down to Earth. And this one gets a star, just meaning that we identify the window specially that will be the last window for which the data will be received in time on Earth to plan the next day's activities. But all the data eventually comes down. After that pass, we have some more remote sensing usually, and then we see that we go through periods of sleeping, waking up for different activities, including later in the morning, close to the next day of activity, we have some morning remote sensing. But we have activities through the night. When we say the rover sleeps, that means we turn off the flight computer. And we need to do that because the flight computer draws enough power that we take energy out of the batteries while the rover's awake or the flight computer's on. So we need to turn things off and go to sleep to charge the batteries. And then this sort of thin green line that goes along in parallel throughout the whole sol, that's our weather station instrument, the META instrument, and it has its own processor. And so while the rover's awake or asleep, it can be doing its own observations independently. But there are times that the rover needs to wake up and talk to it. So we load the observation table to it early in the plan. And then later throughout the sol, we'll collect data from it so we can relay it down to Earth. And then the final thing to point on this slide is those red blocks showing heating. And so Mars, as I'm sure you know, is cold. And so often to use our actuators or electronics, we need to heat them up ahead of time. And so you'll see a lot of heating going on, and we'll usually do things in parallel. So while we're doing the pre-drive imagery, we'll be heating up the mobility actuators such that by the time we finish that imaging and we're ready to drive, the actuators are already ready to go, and we don't have to waste time just sitting there waiting for them to warm up. Okay, so those are the main points. If you please go to the next slide. So the reason we want to have onboard planner has to do with, I hinted at it a little bit about the uncertainty it takes in terms of time to perform activities. There's also uncertainty in how much energy things take and what the actual temperatures will be. And so with respect to time, so certainly things like autonomous navigation is pretty obvious. There's some uncertainty in how long it'll take to get somewhere. But even with imaging, we use auto exposure. And so there is some variance in terms of how long that'll take and how long it takes to compress things and migrate data to our file system. So there's uncertainty there. And uncertainty translates to energy because, as I mentioned, to have the flight computer running, it's drawing out energy. And so if things take longer than expected, it means we're using more energy than we expected. And temperature plays into heating. And so we have to predict the temperatures, what they'll be. And if it gets colder, we'll need to, or we predict things are colder, we'll have to put more time and energy into heating devices. And it can be difficult to make these predictions. And even as we change rover headings, just changing the heading can change thermal conditions because now different parts of the rover are being hit by the sun. And so they're either colder or warmer than they were at the previous heading. And we tend to be fairly conservative on operations because we don't want to, if things take too long, we don't want to cut things off because we'll lose observations. And worse, if we underestimate energy use, we might go too deep into our battery usage and actually damage the battery. So we tend to be conservative, but this means that usually things take less time and energy than we predicted, and we end up having more resources than that go unused that we could have made use of. And there are times in the mission where we will limit what we do on the rover because our models show that we don't have the time or energy for it. But then when we get the data back the next day, we see that we could have done these additional activities. Next slide, please. Sorry, next slide. Yep, thank you. So an obvious answer to that is, well, let's try to move this decision-making about what to do and when to do it on board the rover where we have the most up-to-date knowledge about rover resources. So that's why we've got the Mars 2020 onboard planner. And again, some of these topics we've covered in the past, so I'll just very briefly highlight some of the high points of what onboard planner has to do. So in terms of resources that it manages time, duration, power, both instantaneous power and energy, and it keeps track of minimum state of charge, maximum state of charge. We keep track of data volumes. We have atomic resources, such as like the mast, only one activity at a time can move the mast around, so it has to manage that. And we've got limited number of sequence engines to run our command files. And then there's additional constraints we can put on the plan to say that you can do as much activity as you can get in there, but we want to make sure the battery is at a certain percentage state of charge for the next plan to start, because we don't want to start the next plan where we have to immediately go to sleep to recharge the battery. And then the onboard planner's job is to, given a set of activities that the ground gives it, to figure out which activities it can do, when it can do them, and based on the current state of resources. And there's different flavors of activities, and which vary in terms of what kind of constraints they have to comply with. So mandatory activities, for example, don't need to comply with the handover state of charge, because we're basically saying operations it's their responsibility to make sure that these activities can be done and still turn over the rover with a reasonable state of charge to the next sol. But then in addition to that, the operators can give some bonus activities or extend existing activities to say, do more of this activity or do additional activities as long as you can maintain this level of battery state of charge going into the next plan. And then the onboard planner has the authority to try to add additional things to the plan. Activities can have dependencies on one another. For example, one activity you can say don't start until another one is finished. We've talked about heating already. The system has to manage heating, has to determine when to start heating, how much heating to perform. There's some efficiency trades to make as well. If two different activities use the same devices, it may decide to just preheat once for that and then extend the maintenance heating to sort of merge heatings, and rather than doing two different preheats. So it has to do some reasoning about that. It's managing when to wake up the rover to perform activities versus when to go to sleep to recharge the batteries. And then it actually has to execute and monitor the plan execution. If we can go to the next slide. So the point of all this was basically to sort of emphasize the onboard planner has a lot of work to do. It has to generate plans, which have all those constraints and considerations. We have to execute the plans. We have to monitor plan execution. And we expect that things are going to deviate, even though we're doing this up on board, generating the schedules on board. Things are still going to deviate from these predictions. And we want to be able to respond to that, because the whole point of this is to, as we deviate from expectations, to be able to be responsive to that. One way to respond is generating a new schedule. So that's a good way to respond. We have a whole new schedule that takes into account the latest knowledge of resources, but that's very expensive in terms of computation to generate these plans. So we want to try, and we're working on a RADSIM 50, one of the older flavors, which is 133 megahertz. And we're sharing that with about 100 other flight software tasks with various levels of criticality. So we need to find a nice way to play with those. Next slide. And that gets us into the design and implementation decisions we've made to try to make this balance between responsiveness and reduced computational complexity. And there's three categories we'll talk about. One has to do with techniques for plan generation, another for plan execution, and then finally, the operating system prioritization that we use for the onboard planner tasks. Next slide. And one more. So for plan generation, again, I'm not going to go to the details of the algorithm, but it starts with our algorithm, and we made the algorithm very greedy to limit how expensive it is to generate schedules. So there's no look ahead, there's no backtracking. We get an ordered set of activities from the ground, and we call that scheduling prioritization, and it takes them one at a time. For the first one, it'll try to find a good spot for it in the schedule. Once it's found a spot that complies with all the resource constraints, it then moves on to the next activity and tries to find a spot for it, and so on until it gets through the entire set of activities to be considered. So that reduces the computational expense by not doing backtracking or look ahead, but it does mean that we're not complete. There could be potential plans out there that we're not going to find. We mitigated that to some extent by on the ground, we can search the space of these scheduling prioritizations to try to find an ordering that we think will give the best chance for the onboard system to find good plans when it generates schedules. And then for thermal conditions, we've, because how much time it takes and how much energy it takes to heat devices depends on when you start the activities that will use those devices. And temperatures are always changing in their continuous functions. We've simplified that search by making a simplifying assumption where we discretize the continuous space of temperature changes to a parameterized interval. So for example, 15-minute intervals, we say for every 15-minute intervals, the temperatures are going to stay constant, and then that reduces the amount of search we have to find spots for these activities. Next slide. And then another thing, obviously, that impacts how long it takes to generate a schedule is how many activities that are considered in that scheduling cycle. And so we have to have a limitation on how many activities operations can ask the system to work on. And we called that the considered set. So for example, we might limit it to say 40 activities. And however, what we realized though is as the sol progresses, once an activity starts and executes and goes into the past, then when we generate a new scheduling cycle, we no longer have to consider that activity. It's already done. So it's out of our considered set. So now we're down to maybe 30 activities instead of 40. What we can then do is have a hopper of additional activities that we can then, as activities execute from the past and finish, we can pull in new activities from the hopper and add them to our considered set. So that any given scheduling cycle, we still only have a limit of 40 activities, but over the entire course of the sol, we may be able to have many more activities accomplished, maybe even up to 100, depending on how things go. Okay, next slide. And one more. So then that brings us to plan execution. And the onboard planner system is actually comprised of two major tasks. One is the plan task, which generates schedules, and the other is the plan controller, which executes and monitors the schedules. And we decided to give some amount of scheduling authority to the plan controller so it can make decisions and be responsive to deviations without needing to go through the larger expense of full plan generation. And so we have two different things it can do. It can what we call polling activities. So if the rover is currently idle, for example, a previous activity it was performing finished earlier than predicted, and we're not doing anything, it can look ahead in the schedule to the next thing that we're scheduled to do. And if it can check to see if the constraints for those activities are actually satisfied now, and if so, it can actually move it up and start doing it earlier so that we keep the rover busy. Conversely, if an activity goes longer than we thought it was supposed to go, and that's preventing another activity from starting, we'll push the activity, and with the hopes that soon that activity that's running late will finish, and if it's the activity that is now late is still eligible to start, we'll go ahead and start it, but starting it a little bit late. There's limits to how far ahead we'll pull things and how far we'll push things, and if it exceeds the push limit, for example, we'll do what we call vetoing, which is remove it from the schedule and notify the planner that we had a problem with that activity. That way, we can be responsive to these smaller variations that we expect to be common in our plans. But when we have larger deviations, we do what we call event-based rescheduling. So if activities end much later than expected, or things got vetoed, or things end much earlier than expected, we can, that's the times that we'll take the larger expense of generating a full new schedule. So again, this makes it such that we can, in a more computationally inexpensive way, quickly respond to common and small deviations from the plan, and then save our large or expensive rescheduling for the larger deviations. Next slide. And one more, please. So then that brings us to the final category, which is how do we fit this task in terms of operating system prioritizations with the other flight software tasks. And this is a very small, high-level view of the kinds of tasks we have. As I said, there's really like 100 of these tasks. But common with the real-time operating systems, we pick prioritizations based on the nature of the deadlines that the tasks have. So near the top, we have our critical periodic tasks that have rate deadlines. And then lower down, we have aperiodic tasks with different kinds of lowering criticalities of deadlines. So we had two tasks we need to find places for: the plan controller and the plan, the schedule generator. The plan controller was pretty straightforward. It basically is replacing the control we had for basically starting activities and stopping activities. That's currently done with sequencing. And so the sequencer lived at a 1 Hertz rate group, and that made sense for our plan controller as well. We have pretty much the same kind of time requirements for it. And we also know from profiling that it can easily fit within the work it has to do, easily fits in that 1 Hertz cycle with plenty of room to spare for other tasks that need to happen. So that one was pretty simple to put it in the 1 Hertz rate group, the non-critical 1 Hertz rate group. The plan task was a little bit more challenging. We estimate that when the rover is idle, just sitting there quiescent, it would take between 30 to 45 seconds to generate a schedule. Clearly, when you start doing additional work that interrupts that, it's going to take longer. And there were certain tasks that we knew we didn't want to interrupt. We didn't want to interrupt mechanism actuations. We didn't want to interrupt communications. We've talked about instruments, so we didn't want to interrupt instrument interactions. And typically, when flight software has to talk with our instruments, it's aperiodic, but it's also pretty small, the amount of work it has to do each time. So it's better and it happens frequently when it happens. And so we'd rather let it interrupt the planner because it just interrupts it for short periods of time when it does, rather than having the planner take out 30 to 40 seconds of interject that kind of delay into instrument interactions. So really, and we also knew we wanted it above the stuff that I have here labeled in the background. So really the question was how to relate it to the navigator. That's the autonomous navigator that's used when we do autonomous drives. So if you go to the next slide, please. So there's two options there. We could have our navigator higher priority than our planner. And the benefit here, one of the advantages we have with the Mars 2020 autonomous navigation system beyond MER and MSL is that we've made it such that the navigator, we do it with what's called thinking while driving. And so while wheels are turning, we're actually building hazard maps and planning routes. And as long as the navigator can keep up, we never need to stop wheels from turning. And we actually can drive much faster doing autonomous navigation than previous rovers could do because of that. So by having the navigator above the planner, we always give the navigator the best chance of keeping up so we don't slow down our drives. However, the consequence obviously is the planner then to generate schedules, that 30 to 45 seconds gets split up into sort of very small pieces of CPU time that was going to take it a few minutes to actually finish a schedule. On the other hand, on the right side, clearly if we put the planner above, it then gets precedence and it can take away the CPU from the navigator. But of course, then that means the navigator might stall out the drive. It wouldn't be done in time. Wheels would have to stop. We'd have to wait a little while during the drive to move on to the next segment. Now, because we've provided responsiveness into the plan controller, that means we don't need to replan as all that often. We think maybe once or twice, a couple times an hour, hopefully. And because of that, because of the limited times that we need to regenerate full schedules, we can tolerate those sporadic interruptions of our drive. It won't make that big of an impact on our overall drive performance by having that limited number of times to be interrupted. So next slide. And so then finally, that let us decide to put the planner where you see it here in the scheduling below most everything except above the navigator and above the background tasks. And one more slide, please. So that brings us to the conclusion. So I've presented the Mars 2020 onboard planner. And our expectations is it's going to be able to provide an increase in our productive use of our rover by better managing resources, because it'll have up-to-date knowledge of the rover's resources. And we have many challenges we had to address, but the ones I focused on here, we're trying to find ways to balance making the onboard planner highly responsive and high performance by still playing nice with other flight software tasks and our limited computational constraints. And finally, we're not quite live on Mars yet. We still have some more V&V of the flight system to go and some more ground tool development to work on, but we're hoping towards the end of the year to start rolling this out live into operations. And I'll take questions. If you go to the next slide, I can show you some references, and I can stop and take questions. Thanks.
All right, thank you, Dan. We do have a few minutes for questions. So first one up, are there any plans to port this system back to MSL if it goes well on Mars 2020?
Probably not. You may have saw an interesting talk from Alexandra online already about some R13 updates for MSL. So they are making some updates. This one is probably a little larger than they'd be able to do. There is some flavors of this that they may take. One of is we added a new state of charge estimator on board to estimate the battery state of charge, which our planner needs. I forget if I think they're pulling that in, or they're planning on pulling that in, and they may have already done so. And then they can then use that to help determine if when they should inform shutting down early, so they can try to shut down early and save energy for the next sol plan. So there's a little bit of the flavors that they are thinking about using, but probably not the full system.
Okay. Give a few more minutes, see if any other questions filter in. Got about 3 minutes left. All right, Dan, thank you very much.
Thank you.
Sorry, one question just came in. Is 64 hertz enough for motors?
Well, so that's the rate at which we talk across the bus to the motor controller. The actual motor control, there's a separate device off of the flight computer that actually directly actuates the controllers. I know less about that device, but I believe it's higher rate than 64. But 64 hertz is basically us telling the motor to start running and to stop running.
Yep. Yeah. Okay. Great. All right. Thank you very much, Dan.